Hello, my name is Jacob Coyas,
My name is Ricardo De Luna Lopez.
and we are the team leads of the Project HydroCube here at UCI.
Every year we need more and more energy. However, our natural resources are being depleted. This is why there is a greater push for renewable power sources. One of the main renewable power sources is solar energy. Within the solar energy industry, Tesla, as we know, has created the Powerwall. The Powerwall is a battery system that better manages the use of electricity captured through a photovoltaic cell and stored in a battery. This Powerwall, however, is still using batteries, which means that these batteries will eventually end up in a landfill. This is the reason why our project is investigating power-to-gas energy storage systems.
The overall goal of our Project HydroCube is to create a long-term energy storage system using the excess energy from solar panels. Until now, this excess energy is stored using batteries. Unfortunately, the batteries are not an efficient way to store this energy long-term. To address this problem, we are using this excess energy to split water into hydrogen and oxygen. This hydrogen is then stored in a compressed gaseous form. This is beneficial because the hydrogen gas can be stored for extended periods of time, unlike the batteries, and used later as an energy source.
I'm Octavio Altamirano, a member of the experimental sub-team, and what you're seeing on screen is a simplified schematic of our project. So at the top we have a PV cell, or a solar panel, and it produces electrical input into our MPPT in the form of DC current. An MPPT is pretty much a smart device that dictates where our current goes depending on and off peak times. So on off times, the energy goes into our electrolysis unit, which takes the DC input as work in order to produce hydrogen from water. Then from there, it produces fuel in the form of hydrogen to the home. On the other side, we have battery, which stores the DC current and then distributes it out into the inverter. From the inverter, it goes into the home as AC current, enough to power electrical devices. So as the experimental group, we had a few responsibilities, one of which was to assess and replace the previous battery unit. From there, calculate the idealized power output of the solar panel, and then from there, design the battery based on those requirements from the calculations. All this had to meet our specifications, which were to have a battery unit that was 900 watts, able to store 2.3 kilowatt energy, and cost less than $600, all while being able to put out a voltage of 48 volts or higher, considering voltage drop.
Hi, my name is Eduardo Ambriz. I am the lead of the mathematical modeling subteam. Our goals and requirements are to effectively model our HydroCube. The purpose of modeling the cube is to expose weaknesses in our design and to yield theoretical values we seek. In doing so, we save time and manpower or womanpower and be overall more efficient while satisfying our goal parameters such as volumetric flow rate, the number of cells we plan on using, and voltage.
Hi, my name is Giselle Cardoso, and I'm the SolidWorks Manufacturing Sub-Team Lead. One of our responsibilities for this quarter was the preliminary design for the electrolysis system. We also worked on determining the hydrogen and water flow rates of the PEM electrolyzer, and we also determined and selected the components for the filtration system. We also had to investigate the hydrogen transportation in terms of pipes, storage, and compression, and we also had to work on the SolidWorks modeling of the electrolysis system. One of the requirements that we worked on was for the PEM electrolyzer was its ability to withstand 800 watts. The system must also operate under standard conditions, meaning 20 to 25 degrees in temperature and 1 ATM. And hydrogen gas must be compressed to 20 to 80 ATM. We also must use deionized water with a total dissolved solid range of 100 to 2000 ppm. So this gives a breakdown of the overall electrolysis system breakdown. One of the 4 basic units within an electrolysis unit is water treatment, gas storage, power unit, and the overall electrolyzer module. So in our case, we use a PV cell or solar panel to serve as our power unit. We also use an MPPT controller in order to make sure that the voltage being supplied by the PV panel is at the accurate voltage that the electrolyzer needs. We also needed a filtration system to make sure that our water is deionized to a 2000 ppm TDS value. And with that, we are also connecting it to a water tank in order to store all the water that we need in order to fulfill electrolysis. After the PEM has converted water to hydrogen, we need to compress the hydrogen up to 20 to 80 atm, and with that, it gets stored within the gas tank. So this gives the overall SOLIDWORKS modeling of our system. In the picture on the right-hand top, that gives the overall total assembly of everything combined, and the images below that image show everything that's within the system in terms of the water tank, the PEM electrolyzer, and the hydrogen storage tank.
Here we have the timeline for our project. It is broken down into this year's 3 quarters. This quarter was mainly dedicated to the mathematical model of our HydroCube, the overall design, and improving our battery pack. Next quarter will be dedicated to the manufacturing of the HydroCube. And finally, spring quarter, we will be testing hydrogen production and the overall efficiency of the system. We hope that our project inspires others to research this technology in an effort to move towards a more renewable future. Thank you for listening, and we appreciate it from everyone at HydroCube.
That's a wrap.
That's it.